Okay, good morning, everybody. Let's get started. Just an update on the assignments. Undergraduates, you are now tackling assignment 4 when you're going to be adding the 5th and the 6th set of components to your robot, which is neurons and then finally synapses. So when you finally add synapses to your virtual robot, you are going to close the loop between the robot acting, that having an impact on its relationship to the environment, which causes changes to the sensors. The values arriving at the sensors are sent to the input neurons. The values at the input neurons are transformed by the weights of the synapses into values that are arriving at the motor neurons. The values arriving at the motor neurons send the values to the motors, and the motors interpret those numbers as what? What do the motors do with those numbers? Torques, right? So we're going to treat them as rotational forces, which are being applied for the moment at hinge joints. And hinge joints are going to apply torque, like twisting off the top of a bottle, to rotate or apply forces to cause the orientation of two connected objects to change relative to one another. So the moment that your motors apply those torques, those are additional forces that are acted on the connected objects. And as you remember from our discussion of physics engines last week, the physics engine updates the positions and orientations of the objects by computing all the forces that are acting on those objects. So the values come from the motor neurons to the motors, where they're interpreted as torques. Torques are applied to the objects. The physics engine takes over, computes the new positions and orientations of the objects, which causes changes to the sensor values, and around we go. So when you finish part 2 of assignment 4 this week, you will see your robot actively acting in the environment. And at that point, you can start modifying one or more of the 6 elements that make up the robot. If you change the synaptic weight, what does that do to your robot? What does that do to the behavior of the robot? Changes the torque that's applied to the motors given the same sensor input, which means the robot will react differently if it senses the same thing as it did before the change to the synaptic weight. You can also make physical changes to the robot, elongate or shorten the cylinders, change their mass, change their radii. You can alter the behavior of the robot by either altering physical characteristics of the robot or neural characteristics like the synaptic weight. And as you can imagine, in assignments 5 and onward, it's not going to be you tinkering with the brain and body of the robot, but increasingly powerful evolutionary algorithms that are going to try and tune those aspects of the robot to produce, for the moment, forward locomotion. Any questions about assignments 1 through 4? Graduate students, you're moving on to assignments 7 and 8. All good? Okay, so back to our discussion of the very long history of evolutionary robotics. In lecture 7, we're talking about 2 of the first evolutionary robotics experiments, which were reported in the 90s in the same year. The first by a pair of Italian researchers who used our hockey puck-sized Kepra robot here. They hooked it up to a computer. Computer is going to run the evolutionary algorithm, download a neural network onto the hockey puck robot. The Kepra does its thing on the tabletop, and then we're going to compute the fitness of that robot. Just to refresh your memory, we're going to try and get this robot to race around this maze or this track as quickly as possible. It has 8 proximity sensors and 2 motors. You can see how it's connected up. It's not that much more complicated than a Bratenberg vehicle. And we're now, or I left you with last week, thinking about constructing a fitness function, phi, which can return any floating point value between 0 and 1 after the robot does its action, or after the neural network produces action in the robot. And we're going to try and construct this function as a function of 10 variables, the values of the 8 proximity sensors, which the robot has access to, plus 2 additional numbers, which is the rotation of the left motor and the right motor, which can rotate backwards quickly or stay still, or rotate forward quickly. So this is something to keep in mind as we look at an increasing number of evolutionary robotics experiments. What information does the robot have access to through its sensors? And what information do we as the investigators or the evolutionary algorithm have access to compute the quality or the fitness of the behavior? It's not always the same set. We might have additional information that we can see about the robot's behavior that it itself does not have access to. And this is a simple example of this. The robot has access to 8 numbers, the proximity sensors, which through its neural network drive its behavior. We have access to 2 additional pieces of information, which are obviously important if we want to compute how well the robot is doing at driving around this maze, which is the speed of the wheels. We don't have a video feed of the robot in the maze, just these 10 numbers. How might we go about constructing this fitness function so that it gives us a higher value whenever the robot does a better job of racing around this track, and a lower number when it does a worse job?
Softmax.
Sorry?
Softmax.
Softmax of what?
Like a state value will take input this to the softmax function. It will depending on how it's performing, value from the sensor, it will convert it each time value between some kind of a probability, and those probability will add up to one.
So we're definitely going to do something like that, right? We're going to look at these values and compute a value. It could be softmax, but what in particular? What is the computation we want to do? Let's work backwards from the behavior. If the robot's going to race around the maze.
Could you do maximize generally the values of the proximity sensors so that, or whatever it would need for being far away from walls while having a high velocity of the wheels?
So we want high velocity of the wheels, right? So we want to use VL and VR somehow. So let's try and plug VL and VR in for the moment. Let's try and reward for speed, and we'll worry about the proximity sensors in a moment. So what? How are you going to combine VL and VR? For our purposes, let's simplify this, and let's imagine that VL is the average speed of the left wheel for 10 seconds, let's say, in the maze. We would probably write this as V sub LT, where the T index would be the value of the velocity of the left wheel at time T. We're going to just simplify things here and assume that we got 10 numbers, and they're the mean values of those 10 variables over a 10-second period, let's say. So how are we going to combine VL and VR to select for speed? VL plus VR? Divide by 2, we could do that, that's fine. Seems pretty good, right? So if we did that, if we just set phi equal to VL plus VR divided by 2 and ran an evolutionary algorithm to maximize phi, what behavior are you going to get?
You need to add the eyes.
Definitely going to have to add the eyes because?
Because those are the inputs to the robot.
We only care about behavior.
The robot's going to ram the wall and just keep driving that way.
It's going to ram straight into the wall, right? If we're trying to maximize VL and VR, we're selecting for forward speed as quickly as possible.
Or you could just get it spinning on one wheel because you're adding them, not multiplying them, so it can spin and have one wheel going really fast.
Possibly, right? So evolution might say, all right, VL plus VR, I'm going to forget about one of them and just try and maximize the other one. You might get spin. So for example, it might maximize VL and leave VR as 0, and it's going to spin around its right wheel. But if there's a mutation that increases the speed of VR while not decreasing the speed of VL, that neural network in the population will beat out the neural network that causes it to spin in place. So VL plus VR is probably good enough to get fast forward speed.
Could use a weighted average of speed with the 0 and 1 proximities. Each step they're averaging in speed is 0 if, well, I think it's flipping it, but you count it if you're not bumping into something. Bumping into something, zero it out.
Okay, if you're bumping into something, zero it out. So you said with, right? So how are we going to combine VL and VR? Let's imagine we define a new variable V V equals VL plus VR. So we got one term there, V, which selects for velocity of the robot. How are we going to actually combine algebraically the i's into this?
1 minus I, combine all of the i's together.
Okay.
And then, so for example, if the robot is not seeing any object, all of the i's would give you zeros. So 1 minus I.
So we could do 1 minus I, where we're defining I as the
Accumulation of all
the mean or the sum of all the i's. What is this going to give us? Imagine we wrap an evolutionary algorithm around this. What kind of behavior are we going to get from the robot?
It's going to go straight if it doesn't see any object.
If it's far away from the walls, according to I here, the i's are close to 0, which means this term is close to 0, which means this term is close to 1, and we're pretty good. You'll notice here that we're multiplying the two terms for the reason that you mentioned, right? If it's going fast, but smashes into the wall, then at least one of the i's is going to be 1, because that proximity sensor is registering the wall. And this is going to be at least close to 0, which is going to degrade the value of this.
If we're trying to train it to go around as fast as possible, is this going to lead it to go like in the middle such that it's the same distance from each wall, or is that canceled out by
Good question.
us trying to get it to go faster?
So we're asking evolution already to balance V versus I, right? If the only thing we cared about was I, let's say we just sent this fitness function to the evolutionary algorithm, what are we going to tend to get? What kind of behaviors are we going to tend to get?
It's just going to move in straight lines because it's not biased left or right.
It's going to move in a straight line? What's the best thing the robot could do if we're just penalizing it for proximity values? Stay in the middle, right? So imagine it starts here. It's kind of close. On the proximity sensors on its left side are blinking. So maybe it turns and just tries to move away from the walls, right? This is the coward. It's afraid of walls no matter what. If we add in V, evolution is trying to find something that maximizes V and minimizes I. So it's going to have to strike a trade-off, right? So let's talk about I for a moment. How do we combine our I1 through I8 into I? We want it to avoid the walls.
Give more weightage to the sensors that are in front.
Possibly.
Probably you bump head on first. And then
Possibly. We could weight the ones that are most anterior or towards the front of the robot.
You could average them.
Could average them. If it comes up against, for example, this spur here, this little outcropping, maybe one of the 8 eyes goes to 1, it's seeing the wall, but the others are okay, right? So only one of the 8 is complaining. If we take the average, can we do better than the average?
Mean squared.
Mean squared? What do we really care about? Do we care whether the robot smashes into the wall so that one proximity sensor detects that crash, or 3 or 5? Does it matter?
Do you take the lowest side?
Take the lowest, actually the maximum, right? What we really care about is the proximity sensor that registered the biggest hit, right? Even if all the others are silent, if I hit something, that's all that matters. So let's take the max of all of these, 1 minus the max of all 8 times V. Is that enough? Are we going to get something that races around the track? We mentioned back at the beginning of the course this idea of perverse instantiation, which we're going to see many times in this course. And the idea here is, does the evolutionary algorithm instantiate the behavior we want, but in a perverse way, not the way we actually wanted? Can you imagine a behavior for this robot that does not race around the track and does a pretty good job of maximizing this function.
It moves as far away from the wall as possible, then spins in place really, really fast around its center point.
It could spin around its center, but remember V is selecting for forward speed of both wheels. So that doesn't, if it's, the more time it spends spinning on the spot, the lower V goes. So spinning on the spot is actually selected against. We'll use some terms from evolutionary biology like selecting for and selecting against, which is short form for evolution not favoring things that decrease the fitness function. Right? Okay, so spinning in place is selected against. That particular perverse behavior is going to be weeded out by this fitness function.
To go back and forth along the same line?
Could go back and forth, right? It races forward along the current part of the track, quickly does an about face, and then races back in the other direction and back and forth, back and forth, back and forth. That would do a pretty good job of maximizing this function, right? An evolutionary biologist almost 100 years ago said, evolution is smarter than you are, right? Whatever you come up with as a fitness function, an evolutionary algorithm in our case is probably going to find a way to cheat somehow. Okay, what did the researchers themselves do? Something pretty close to what we just discussed, but also has some additional twists to it. And as you can now guess, those additional twists are there to try and weed out some of these perverse behaviors. Let's start with the term V. In our case, we summed it, but in the case of the researchers, they summed the absolute values of the two. Seems odd. Why? One of the long-term goals of evolutionary robotics is to make few assumptions about the eventual behavior. We want to try and build in as little of our biases as possible, but at the same time avoid perverse instantiation. By taking the sum of the absolutes of the two V's, the researchers are actually making less assumptions about the eventual behavior than we did when we defined uppercase V to just be VL plus VR. Why? Go backwards. We all immediately assume that we want the robot to go forward, right? Because we have eyes in the front of our face and we tend to walk forward more often than we walk backwards. Every year when we do this exercise, students tend to want the robot to go forward because that feels comfortable to us. That's the obvious way to perform useful behavior. Thinking about thinking is misleading, right? We talked about it a few weeks ago when we were talking about free will, a very esoteric, abstract philosophical idea. Here's the nuts and bolts where thinking about thinking is misleading. The robot has two proximity sensors on its back. It can see behind itself. Why shouldn't it travel backwards? If that's a good solution, go for it, right? We want to make as few assumptions as possible. So if we just have V in there, it's selecting for going forward, going backwards, but it does not guard against spinning in place, right? We take the absolute value of 0.5 plus the absolute value of minus 0.5. That's 0.5 plus 0.5 is 1. That's excellent. The left wheel spins forward as quickly as possible, and the right wheel spins backward as quickly as possible. So V is not sufficient. So they built in, or they defined another variable, delta V. What is delta V doing?
Making sure that both wheels are spinning in the same direction.
They're spinning in the same direction, right? So if you look at delta V, the more different VL and VR is, the bigger delta V is, the bigger the difference in the velocity between the two wheels. And you'll notice this form of 1 minus. You'll see this a lot as we move forward. You'll see terms in fitness functions that are 1 minus or 1 over 1 plus. Those are penalty terms, right? Whatever the thing is, the variable that's in that term, it's usually something that has a minimum value of 0. and we want evolution to get it as close to 0 as possible. Right? So 1 minus delta v will penalize for delta v, will penalize for differences in velocity. So combining v and 1 minus delta v will maximize the speed of the wheels and minimize the difference between them, which will give us either fast forward or fast back travel. So far, so good.
Does the 0 and 1 for v imply like 0 is stationary and 1 is forward, or
Correct.
backwards?
Right, so remember that stay still for a VL or VR is 0, right? So again, you're going to be constructing your own fitness functions, quite a few of them towards the end of the term. It's useful to try and create terms that vary between 0 and 1, where 0 is bad and 1 is theoretically optimal. Multiply them together, make some of them rewards, some of them penalties. There's an additional twist here, which they took the square root of delta v, so we can convince ourselves that delta v is a positive number, so we're not going to end up with imaginary numbers in our fitness function. Why do they take the square root? Well, if you remember the square root function, it increases very quickly for very small values and then flattens out. So by wrapping delta v in a square root, we're increasing the amount of penalty for any deviation away from 0. So we're kind of increasing the magnitude of the penalty for any slight difference in v. We really want this robot to go straight at all costs. Unless one of the infrared sensors, the proximity sensor, starts complaining. So this 1 minus I term is pretty much what we just described, 1 minus the maximum value of the eye sensor. So as the robot is doing its thing for 10 seconds on the racetrack, if whatever sensor complains the most during that 10-second period, that's included in this penalty term.
Doesn't that, I know it's a far-fetched thing, but if one of the sensors faulty, doesn't that
Says the engineer, right? What if one of the sensors is faulty? The worst case scenario that keeps roboticists up at night and engineers as well is what if a sensor is faulty, right? Tricky. Maybe. How would you penalize, we'll leave this for the engineers, how would you complexify your fitness function to penalize for faulty sensors, or at least detect and discount a faulty sensor? Not a trivial thing to do. Yes?
A logic statement that that's our range of expected values.
Possibly, we could say here's how we expect the sensor to behave, and the further you deviate from that behavior, the more penalty, or the more we're going to discount that value, assuming we know what the expected behavior of the sensor is in a given situation, which in a lot of practical situations we don't quite know. Not an easy thing to do. Could be a good idea for a final project for those interested in this. Okay, so turns out this the fitness function you just saw is pretty good. This was done in the 90s before physics engines existed, so they did this with the actual Kepler robot in this maze. It took to evaluate one generation, so to take a population of random neural networks, drop each one into the physical Kepler and record phi for each of those neural networks. Took about 40 minutes. They did a total of 100 generations of an evolutionary process, which took a little less than 3 days. This was an extremely painstaking experiment, as you can imagine. Every individual neural network took whatever that is, maybe less than a minute. They had to reach in, grab the Kepler, bring it back to the center, do it again for a total of 3 days. Very painstaking. You can imagine the researchers involved in this experiment and those that came after them said, there's got to be a better way to do this. And then physics engines came along, which we'll talk about later. Okay, so again, apologize for the quality of this plot, but we have evolutionary time along the horizontal axis here, the number of generations. The vertical axis is fitness, or phi, which ranges between 0 and 1. The upper curve is the max, the value of the best neural network in the population at that time, the neural network that had the highest value of phi, and the lower curve is showing the average values of phi across all the neural networks in the population at that time. You'll notice that after 3 days, it was only at 0.25 phi. In theory, maybe there's a neural network out there that would obtain a phi near 1. They never even got close. Is that because the evolutionary algorithm failed? Or because of this trade-off, that there's no way to maximize V and minimize I simultaneously, right? Most of the problems that we want our robots to solve is a trade-off. Do this task well without harming humans, and it has to try and strike a balance, and hopefully it weights the second term more than the first term. But it's a tricky thing to do in practice to get an autonomous machine to balance all of the things we want it to do well, and we'll come back to that later. Okay. You'll notice here that the best robot actually does race around the track. Each of these line segments is cutting horizontally through the robot. So at every point in time, we can see its position, we can see it racing down here, and then detecting the oncoming wall and doing an almost 180, and then heading up the other branch of the track, and away it goes. Question?
Do they try the same robot with a different orientation of track?
Good question. So we could take the same track, put the robot somewhere else in the track, and see how well it does. Or we could modify the track itself and see how well it did. Given the amount of effort it took to do this, I do not think they did it, or at least they didn't report it in this paper. So we have no way to know, in general, how good this robot is at navigating racetracks. Okay. Here is the same data, but now, again, we have evolutionary time on the horizontal axis, but now we've broken out the value of the 3 terms, v, 1 minus I, the dashed line, and 1 minus square root of delta v, the dotted line. How did evolution, in this case, go about trying to reconcile these 3 terms? Did the evolutionary algorithm improve all 3 elements of the behavior at the same time? Kind of hard to say, right? So the solid line is gradually increasing over about the first half of the evolutionary trial, which tells us the wheels are turning faster. We at least know that. We can see, if we look at the dotted line here, that delta V is slowly coming down, which means evolution is straightening the trajectory of the robot. And 1 minus I is kind of bouncing all over the place here, the dashed line. So it's getting closer and further away from the wall of the track as it goes. Okay. They also tried to visualize this in 3-dimensional space. You can stare at this at your leisure and see if you can try and pull out of this how evolution was reconciling these 3 elements of the behavior. Okay. One of the interesting things they noticed is this one evolved individual that sometimes it would start and would drive directly into a corner, and then it would always turn left, which is good if you're on a circular track. They took the same robot, they pulled out the best evolved neural network, and they plugged in a handcrafted neural network, which is a Bratenberg vehicle. So if you look carefully, you'll notice the widths of the synapses. Some of them are broader than others, which tell you the weights are stronger. So if we look at, for example, the left motor neuron here, it's receiving values. There should be 8 incoming arrows. The incoming arrows that are more anterior, closer to the front of the robot, are thicker, meaning they have stronger weight, and the ones at the back slightly less. You'll also notice, if you stare at this picture long enough, the heads of the arrows, some of them are triangles, which means excitatory connections, and some of them are this other shape, which represent inhibitory connections. Remember that for our purposes, excitatory weights mean positive weights, and inhibitory weights mean negative weights. You'll notice that the outside synapses that are arriving at the left motor neuron are excitatory connections, and the contralateral connections, the ones coming from the sensors on the other side, contralateral, are inhibitory. Where have you seen that before? It's a Bradenberg vehicle.
Is it the attacker?
Is it the attacker? Does it want to attack proximity?
No, it's a coward, right?
It's the coward. It's afraid of proximity, right? So the more proximity, the more that it will spin the wheel on that side, which will cause it to turn away from the proximity, right? Okay. The Bradenberg vehicles, all of them are bilaterally symmetric. The pattern of weights on the left side looks exactly the same as the right side, as you can see in this picture here. For humans, bilateral symmetry is a good thing, right? We're bilaterally symmetric. That's always a good thing. Thinking about thinking is misleading. Symmetry in some cases is bad. For example, if you take this Bradenberg vehicle and point it directly into the corner, it'll try and turn away from the proximity, in which case there's more proximity on its left. It'll turn back, and it grinds to a halt, right? As the coward does. The evolved neural network is almost symmetric, but has a little bit of asymmetry in it, which the researchers thought was just kind of leftovers from the evolutionary process. Evolution is not an optimizer. She doesn't produce perfect solutions. She's a satisficer. She produces things that are good enough for what they need to do. So the slight asymmetries they thought was just, leftover. However, it turns out in this case that it's not. It's intentional. It helps to be slightly less than bilaterally symmetric, at least for this simple creature, which for our purposes, again, is just a reminder that thinking about thinking is misleading. The physical structure of the robot is perfectly bilaterally symmetric, but the brain was evolved to be slightly less so that it knows what to do when it comes to a corner. It will always turn left or always turn right. Okay, another interesting thing they noticed is that this evolved controller drove the robot at a maximum speed of 48 millimeters per second. But if you set both wheels to go at their maximum speed, the robot could travel at 80 millimeters per second. Why didn't evolution produce something that raced around the track at, again, it's not an optimizer, but much closer to 80 millimeters per second? Why the slower speed? It couldn't do that great a job with V. Why?
Well, you need to take sensors into account, and
The sensors are not that fast, right? You might think that if it travels at 80 millimeters per second and has to turn to go around the track, that maybe it would tip over. The nice thing about the Kepler is it has a very low center of mass. It was the Lamborghini of robotics back in the 90s. Can take turns very quickly. The proximity sensors on board this robot, they update at a certain frequency, right? It's obviously much faster now in modern robotics, but the robot could only see proximity values at a certain frequency dictated by the speed of refresh of the sensors. And if it traveled too fast, the wall would be far, and at the next refresh of the sensors, the robot has already crashed into the wall. So without us telling the robot what the maximum refresh rate of the sensors is, it's indirectly taking that into account when it's optimizing the behavior. Most evolutionary roboticists are lazy. We don't want to have to tell the robot or the evolutionary algorithm everything about the nuts and bolts of the robot. Let evolution figure out how to trade off not just the different things we want the robot to do, but the limitations of the robot itself. Okay. All right, let's jump across the English Channel to Brighton and the University of Sussex, where at about the same time, another evolutionary robotics experiment was carried out. It was very different and produced this very Rube Goldberg-like looking robot. Doesn't even look like a robot at all. Let's talk about the robot first. As you can see, the robot was basically a trolley. They took a table, they sawed out the top of the table, and then they put on top of the table the X trolley. And the X trolley has a motor on it, which turns the wheels of the X trolley, which causes the trolley to move back and forth along the X axis of the table. They then put a smaller Y trolley on top of the X trolley that would drive along the Y axis up and down the length of the X trolley at the same time that the X trolley is moving. So we have two motors at the moment, one driving one trolley, the other motor driving the other trolley. They then took this funny mechanism and dropped it down through the belly of the Y trolley. It's a camera that's pointed down. And here's the camera here, and the camera is pointing down and is pointing at a small circular dental mirror. And that dental mirror, as you can see, is angled at 45 degrees. And the third motor can rotate the dental mirror. It's basically an upside down periscope. So what does this robot see? It sees underneath the table, and thanks to this rotating dental mirror, it can look horizontally at just above the floor under the table. And as you can see here, they can obviously, like the previous experiment, they can put obstacles and other things into the robot's environment. Why the heck would you make such a crazy contraption? What is the advantage of this over this? We're going to, as you can imagine, in the previous one, we're going to evolve neural networks, and those neural networks are going to control these three motors. They're going to move the two trolleys and move the dental mirror underneath. And we're going to create a fitness function that selects for it to move about and do things under the table. Why do it with this robot? Let's say I divided the class in half. One half is going to work with the Kepra, and you're going to have 3 days, and every 40 seconds for those 3 days, you got to grab the Kepra and put it back to the starting position in the track. The other half of the class is going to work with this robot. Why do you want to be on the second team?
It just reset itself.
It resets itself, right? So you can send commands to the three motors, which will reset the robot automatically. You don't have to reach in every 40 seconds for 3 days and reset it. Okay. What does the robot see? We have this dental mirror. Remember, we have this rotating dental mirror underneath. Before we talk about what it sees, the robot also has this bigger disc underneath. This bigger disc has a larger radius than the inverted periscope. So as it's moving about under the table, if it collides with anything, it will bump this disc, which will cause the arm of the disc to deflect. And that deflection angle is detected by a sensor. So the robot can detect whether it's bumped into something front left, front right, and back left. So it could actually probably figure out exactly the angle at which something hit it. For our purposes, we're just going to boil this down to, did it get hit front left, front right, back right? What does it see? We're getting this video feed from the robot. This was carried out in 1994, so no real-time video processing at all. So they simplified what the robot saw as follows. They took the CCD image coming from one frame of this video feed. So the robot's north, its west, its east, and its south. They transformed the coordinates into a circular picture. They then took all of the pixels, they threw away the color, they threw away RGB, They took the grayscale and they further reduced the grayscale to an integer between 0 and 15, where 0 is black and 15 is white. So we're throwing away a lot of information. They then, within this circular receptive field, so a receptive field is basically the area in which the robot or the organism can see, they placed 3 circles at 3 different positions. And these 3 circles had larger, smaller radii. And they then averaged the grayscale values inside these 3 circles. So again, seems like kind of an odd thing to do. The mammalian eye actually does something quite similar. You have a mass of photons that are falling on your retina, but you tend to only focus on a receptive field which sits right at the center of your overall receptive field. It's known as your fovea. So it looks to you, again, thinking is misleading, it looks to you like you're getting a relatively high resolution feed all the time, but what you're really getting is only a focused image of about 3 to 5 degrees away from center of where you're looking, and everything else is a blur. But you're rapidly looking at different positions in your visual field and picking out different details, and your brain is stitching that into an illusion that you're seeing everything in relatively high resolution simultaneously. You're not. Okay, so we have 1 fovea. This robot has 3. It can focus on 3 different areas within what it's seeing under the table. Okay, so we really have, what we're ultimately going to feed into the neural network are 7 sensors. There's going to be 4 bump sensors, which are either 0 or 1. If we detect bump from any one of these 4 quadrants, we turn the 0 to a 1 for that sensor. The 5th, 6th, and 7th visual sensor coming into the neural network is a value between 0 and 15, which is the amount of whiteness inside that circle. So at every time step of the operation of this robot, it's getting 7 numbers. So far, so good? Okay, and as we just talked about, it's going to transform those 7 sensor values into 3 output values, which are commands to move the trolley, the X trolley, the Y trolley, or rotate the dental mirror underneath it. Okay. Again, seems a little bit odd. Let's have a look at the fitness functions, plural in this case. They actually evolved the robot to do 3 things, phi 1, 2, and 3. And this was one long evolutionary algorithm. They're going to run it, and for the first third of evolution, they're going to use phi 1. For the second third, they're going to use phi 2. And for the last third, they're going to use phi 3, which is a technique we're going to see many times throughout this course. They're going to swap in these different fitness functions, and as you can kind of guess from the cartoon here, these different fitness functions select for increasingly challenging behavior. In the first case, they're going to evolve the periscope from 2 different initial positions. They're going to evaluate each neural network twice. In one case, the neural network starts here. In the second case, the neural network starts here. And in both cases, the periscope just has to go towards the back wall of underneath the table, which is painted black. Go towards black. Just go towards the back of the table. Not that hard. Then they're going to do the same thing, but in this case, they're either going to place a black rectangle back right or back left. And the periscope has to go to the black triangle. Black rectangle. In the third case, they're going to put either a black rectangle and a black triangle towards the back, and they're going to change the order at which they're put. Sometimes the rectangle's on the left, sometimes the rectangle's on the right, and the robot must avoid the rectangle and go towards the triangle. So it's going to have to start distinguishing between shapes. Why not just evolve for the entire time using phi 3? If what you ultimately want is something that can distinguish between black shapes, why not just start with that?
maybe this method ups your process of training it, or essentially as the generations go by, they will be much more smarter at that, rather than just starting the problem.
Why don't we just start teaching differential calculus in kindergarten, right? Why all this intermediate stuff with painting and nap time, and let's get to the good stuff, right? Turns out that for most organisms, and robots as well, we need to scaffold their experience. We need to start by challenging them to learn easier tasks, which we think are going to be the building blocks for more intelligent behavior, which should immediately be setting off an alarm bell in your head by now, which is thinking about thinking is misleading. We think go towards black, then go towards black rectangles, then distinguish between black triangles and black rectangles is a good curriculum in which to learn things. We could be wrong. In this case, they got lucky. It was right. Yeah? We're going to see this idea of scaffolding many times throughout the course. This is an idea that comes from psychology. It comes from developmental psychology, the study of children. Obviously, developmental psychologists and educators are very interested in how best to scaffold the learning of an organism, a young human, or in our case, an autonomous machine. Okay, so not very complicated fitness functions here. They're going to use this should be y sub I, which is the perpendicular distance from the opposite wall, the front wall. So they're trying to maximize the distance from the front wall and get it to go towards the back. You'll notice that they're summing 4 times. In the cartoon here, I'm showing 2 initial positions. They actually evaluated every neural network 4 times. I'm sorry, I misspoke. Every neural network is evaluated 4 times. They automatically move the turret to a random position under the table and let it go. And they take the average ability of the robot to do what it's supposed to do under those 4 conditions. So unlike the racetrack robot that we just saw, we're selecting for generality. The robot ultimately should be able to distinguish between rectangles and triangles, regardless of where it starts and regardless of where it starts looking. Okay. The second phi that takes over, the second fitness function, is going to select for minus di, which again is another way to just penalize di, which in this case is penalize final distance between the turret and the center of the black rectangle at the back. There's different ways you could do this. Again, you're going to get in the habit of writing lots of fitness functions. You might think of easier ways to do this. In the final fitness function at the bottom here, we've got 2 terms. We're subtracting one from the other. If you look at the first term, which involves the D1s here, it's the distance of the rectangle or triangle at the starting point minus the distance of the rectangle or the triangle at the end point. They're trying to maximize the term that starts with alpha and minimize the term that starts with beta. D1 refers to rectangles and D2 corresponds to triangles. Would have been easier to probably write this as D sub R for rectangle and D sub T for triangle. But as you can probably see from this, we want to minimize the distance to the triangle and maximize the distance from the rectangle. Everybody see that? Not that complicated. What are the alphas and the betas for? Why do you think those are in there? Sorry? We're penalizing B and rewarding alpha, beta and rewarding alpha. What are alpha and beta for? Weighting. They're weighting terms, right? So imagine that we set, at the beginning of this experiment, we set alpha to 1 and beta to 0. What behavior do we get? It always goes towards it maximizes the distance from the rectangle. That's all it cares about, right? It's the coward. Wherever you put it, it'll go in the opposite direction from the rectangle. If we set alpha to 0, and we set beta to 1, and run the evolutionary algorithm, what happens? Say that again? It'll attack the D2 is the triangle. Alpha is 0, beta is 1.
Or it will go far away from it because of the negative?
We still have the negative in there. So negative beta, negative 1 times this term. We're minimizing the distance to the triangle. Wherever we put it, it's going to try and go towards the triangle. If we put it right next to the rectangle, it'll skate the side of the rectangle and go straight to the triangle. It's not afraid of rectangles, right? We want it to be fearful of rectangles and love triangles, right? And by setting different values of alpha and beta, we can sort of weight the fear and aggression part of this behavior, right? So in this case, the investigators have taken on the task of trying to help balance these things. So for certain, we want to try and set these weights to balance these things so that we get something that runs away from the rectangle and towards the triangle. And that's more or less what they got. So let's have a look at the upper left panel here. We're looking down through the hollow table. We've got a triangle at the back left and a rectangle at the back right. And we're going to rerun the best neural network from the population. The one at the end that had the highest value of phi 3. We're going to start first by putting the turret here and letting it go and let the neural network control it. Then we're going to put the turret here. Then we're going to put it here. Then we're going to put it here. This one is not that great about avoiding the rectangle. Maybe we should have weighted the beta term or whichever alpha term a little bit more strongly. But it definitely loves triangles. What else can you tell me about the behavior of the turret here? The behavior of the neural network that it produces in the turret.
Like certain starting points.
In some cases it goes straight, and in other cases it's actually rotating the dental mirror, or the trolleys are both moving so that it describes this corkscrew as it's moving. Seems kind of odd, right? We want the robot to go more or less straight towards the triangle, but it's doing this dance. It's not optimal. Clearly, this is not an optimal design. So again, is this because evolution is just satisficing? Or is there some advantage to the corkscrew? Okay, hard to tell at the moment. So let's break open the trolley bot here and look at this evolved neural network. What is inside? Well, this is drawn a little bit differently from what you've seen before. Here are supposed to be the seven input neurons, but in this neural network, it only used 2 of the 7. The synapses connected to the other 5 were so close to 0, they're basically not there. So evolution has said, I don't need all 7. I only need these 2, which are V1 and V2. So it's only using 2 of the 3 circles back here. I'm sorry, I forgot to mention one other detail here. My mistake. In everything we've seen so far, evolution is only tuning the synaptic weights of the neural network. In this experiment, they broadened the evolutionary algorithm a little bit so that each genome in the population encoded numbers or weights for the synapses, plus 9 additional numbers, which is the X and Y position of each of the 3 receptive fields, plus the radius of that field. So X1, Y1, R1 describes the position and size of receptive field 1. The second triplet, X2, Y2, R2, the position and radius of the second receptive field, and the third one. So evolution is tuning the brain of the robot, but it is also tuning and placing where the robot looks inside its receptive field. Evolution also placed our fovea as well. Why did the researchers do that? Well, we'll see that in this slide here. In this particular case, evolution threw away the bump sensors, because obviously bump sensors don't really matter for this task. There's no obstacles, so it doesn't need them. It also only needed 2 receptive fields, and these are the two fovea, and it placed those 2 fovea here. This is described as the visual morphology. So morphology, for our purpose, is just a fancy name for shape or organization or distribution. So evolution has said, I want you to place 2 receptive fields here, and they get wired up like this, and they connect to the 3 motor neurons, the 2 trolleys, and the dental mirror. You'll notice synapses flowing from the input layer to the output layer, and you'll also notice some neurons in the middle here. So if you recall your discussion with Joshua Powers when he walked you through neural networks, we have input neurons, output neurons. What are these ones in the middle called? This is the hidden layer, or hidden neurons. Why are they called hidden? Because they're hidden from the real world. They don't directly sense anything from the real world, like the input neurons, and they don't directly influence the physical world, like the output neurons do. They're hidden. They're in the middle. We also have solid lines, which are excitatory connections, and dotted lines, which are inhibitory connections. And you'll also notice there are some synapses that are flowing upstream, back towards the hidden layer. You also see some recurrent connections. Again, trying to recall your discussion with Josh P. about neural networks. What do recurrent connections do? Sorry? They are sometimes used in backpropagation of error, but we're not doing backpropagation of error here. They are propagating signals back up towards the input layer. That's true. What's the advantage of them? What does a neural network with recurrent connections, what is a neural network with recurrent connections able to do that a neural network without them cannot do?
Reset the weights?
Not quite reset the weights. Evolution is going to be responsible for playing with the weights. It remembers, right? So the sensor values are coming in at the rate they're coming in, and they're flowing down to the motors. And if there's no recurrent connections, the moment the values leave the motor neurons, that's it. There's new stuff coming in and flowing down. There's no ability to hold on to any information from the past unless you have these recurrent connections, right? You've probably seen a rushing river where it has these eddies that are flowing, and there's a log that gets stuck and gets pulled back and holds its position, right? It's a memory. A neural network with recurrent connections can hold information from the past, which seems odd for this task. Why does this robot need to remember anything? All it needs to do is look at these 2 shapes, figure out which is the rectangle, or which is the triangle, and go towards it.
Like the shape of the triangle and rectangle is different. Like we need to have the sense like which is triangle and which is rectangle. That's why it's made a bigger part.
Yep, we're getting close.
It approaches it at different angles.
It approaches these pairs of objects from different angles, but that doesn't strictly mean that you need memory, right? If you put me anywhere in the room and ask me to walk towards the clock, I don't need to remember anything. I look at the clock and go towards it. So it's not strictly about the fact that we're evaluating it multiple times. Let's go back and look at the robot's eye. Where is the triangle recognition circuit in here? Where is the rectangle recognition circuit in here? Where's the neuron that lights up when it's looking at a triangle? And where's the neuron that lights up when it's looking at a rectangle? If you've ever studied neural networks that are trained to recognize cats in YouTube videos, at the output layer, there's a neuron that lights up. And then if it lights up, it means there's a cat in the video feed. Where is that in here? As you can probably guess from the question, it's a trick question. There is no neuron that lights up when it sees a triangle or sees a rectangle. How does it go towards the triangle and avoid the rectangle if it doesn't have a local computation to figure out where the triangle is and where the rectangle is? Look carefully at the placement of these two fovea, and they might give you a hint. Thinking about thinking is misleading, so you need to see this from the point of view of the inverted pendulum. The robot is moving and rotating through its environment. How does it distinguish between I'm looking at a triangle and I'm looking at a rectangle? This is extremely hard to see this, and this is why we need to use something like an evolutionary algorithm to design embodied systems. It's very non-intuitive.
Could it be because when it's seeing a triangle, one sees the shape, but two doesn't because of the diagonal placement, but if we get the rectangle, they both hit the rectangle?
Exactly. So if you think about these two circles here, at the moment they're white. So let's assume the robot or the dental mirror is pointed away from the rectangle, but it starts rotating towards the rectangle and hits the right edge of the rectangle. From the robot's point of view, it's a vertical line. It can't see the vertical line. All it sees is that this fovea 1 suddenly goes dark, and a short period later, when the second fovea hits the right edge of the black rectangle, it goes dark. Yeah? Okay, that's fine. Imagine instead the exact same robot with the exact same neural network. It doesn't see anything, and this fovea hits the right edge of the triangle, and then the second fovea hits the right edge of the triangle. What is the only thing that's different from the robot's point of view in those two cases? 1 goes dark, then 2 goes dark in both cases, but...
Well, 2 is lower or higher than it would go dark for a short amount of time.
A short amount of time, right? Shorter amount of time, exactly. The time between 1 going dark and then 2 going dark during this rotation is the signal. But if it has to take time measurements and compare a time interval, it has to be able to remember when 1 went dark, right? So in this case, it is using memory, and it is recognizing objects in a very non-intuitive way, right? This is not, if I were to ask you how you recognize objects, if I asked you to describe a triangle and a rectangle, you'd tell me something about angles and number of sides, which is the answer I'm expecting. But what your eyes are actually doing when you look at a black triangle is your eye is saccading to different points on the shape and remembering what it sees through the pinhole camera of your fovea. It sees a little patch of black and a little patch of white. You jump and look at something else on this dark blob, and you get another local picture. You jump again, you jump again. You're taking snapshots at different positions and doing some computation over those local visual features. That's really, to your brain, what a triangle is. But when I ask you to describe what it is, you give me a very different story. Thinking about thinking is misleading. Yeah? I think in everything we're going to see in this course, this evolved neural circuit is the best poster child for what embodied cognition is and why it's useful. We have a simple circuit here. If you wanted to train a neural network to recognize triangles and rectangles from different positions, you'd probably need many more neurons and synapses than this. But if you let evolution come up with non-intuitive solutions that arise out of the action of the robot with its environment, the robot pushes against its world, it rotates the mirror and detects differences in timing events. If you let it push against the world and observe the sensory repercussions of those actions, it can get away with a much simpler control circuit. The cost, of course, is that it's very difficult for us to understand how this works. Okay, Any questions about that before we move on? Yes?
So the 1 and 2, so if the 1 lights up, does the robot recognize that 1 is a rectangle and 2 is a triangle? Or 1 and 2 are
1 and 2 are just the numbers for these foveas. If you were to really, quote unquote, ask this robot what a triangle is, it would say it's something in which when I do this, when I rotate like this goes dark and then this goes dark at usually this much later, 2.7 milliseconds. If you ask what a rectangle is, it says same thing. When I move like this, these two circles go dark at this time interval. That is what a rectangle is to me. It doesn't know anything about 90-degree angles and 4 sides versus 3 sides. That's its understanding of what triangles and rectangles are.
Does that mean that that wouldn't work if you change the size of the rectangle and the triangle with the robot saw?
Good question, right? What happens if we didn't do any more evolution, just put a bigger triangle in there? Same relative angles. Would it work? Would it not work? I don't know. It's a good question. Maybe yes, maybe no. Hard to say. Doesn't mean that this circuit is any less robust than training a neural network in the traditional way of showing it 1 million photographs of triangles and 1 million photographs of rectangles. That could be a question we could put to an experiment. Hard to say at this point. Yes?
So the rotation that we see on the right-hand side,
Yes.
is that the robot complete trying to locate the rectangle?
Exactly, right? So, thank you. So the corkscrew probably is not just something left over from evolution. It is an adaptive mechanism. It is part of the robot trying to figure out where the triangle is and where the rectangle is. It's actively scanning its environment. You can probably think for yourself of lots of examples of organisms that do the same thing, right? Unfortunately, we put you in a seat and have you sit quietly and absorb material, but most organisms don't learn that way. They go out in the world and literally push against the world and observe how the world pushes back, right? Another question.
Yeah. Does it always have to it always gets one rectangle and one triangle, right?
Yes, that's right.
So does it always have to recognize both, or is it smart enough to be like, oh, I found the rectangle, I can go to the triangle now?
I don't know. If you put it here and it's pointing between the two and it sweeps left and sees the triangle, does it know that the rectangle is on its right without seeing it? I don't think so. But again, you could try this in PyroSim and see what happens. Okay. All right, so let's move on. We will at least start for today. We will start our next theme, sub-theme, on minimal cognition. So as I mentioned last time, in these early experiments now, that came after this pair of experiments, there were sort of two branches that broke off and pursued evolutionary robotics along different tracks. In L8, 9, and 10, we're going to look at the minimal cognition group. Their stated aim, like you just saw in the previous robot, was what are the simplest situations we can create where if somebody looks at the evolved robot, they might attribute cognition to it. It looks like the robot is starting to distinguish between shapes, plan ahead, remember, hold on to that, selectively attend or selectively pay attention to different things in its environment. What you're going to see in these experiments is basically a physical version of the Turing test. Remember, Turing said, listen, it's impossible to define intelligence. How do we infer intelligence among our fellow humans? It's not based on what's in their head, because we don't know what's inside their head. It's based on what they do, or in the Turing test, what they say. Same thing in the minimal cognition experiments. Okay, so let's at least start in on this. We're going to start, first of all, by looking at the particular kind of neural networks that are used in the minimal cognition experiments. They're a bit of a mouthful. They're continuous time recurrent neural networks, or CTRNNs. As you'll see, CTRNNs are a little bit more complex than the traditional neural networks we've been talking about so far, which seems kind of against the whole spirit of this team. So we want to try and make everything minimal, but they're going to start by introducing a slightly more complex neural network. We'll see why next time. We got 5 minutes left, so let's get through the most painful part of this course, which is the only time you're going to see calculus in this class. Okay, just to remind us about why calculus exists. It doesn't exist to torture undergraduates. It exists because there's a problem in mathematics. If we want to describe how one variable changes, like y, as a function of the change of another variable x, it's easy to do if the two variables are changing by large amounts from one observation to the next. So if we write down a difference equation and we say that the value of x at the next time step is the value of x at the current time step plus 1. Okay, that makes sense. So whatever this x thing is, it's going to increase by 1 every time, and we'll just call that change here y. But if x is changing at smaller and smaller amounts, it gets difficult, right? So if we want to try and describe this at a higher resolution, the value of x at 0.5 seconds into the future is going to be the current value plus 0.05, 0.01, 0.01. What happens when our time increment gets down to 0? Undefined, right? Mind equals blown. What do we do in this situation? Thankfully, our mathematical predecessors introduced the idea of the differential equation, which is a way of describing continuous change over time. So the rate of change of x as a function of time equals 1. If we integrate this differential equation and we unroll x over time, we can see that it's increasing in value over time, right? So we can describe things with difference equations and differential equations. Continuous time recurrent neural networks, the CT here should give you a hint. We're going to try and create neurons where the values in those neurons are changing continuously. And we're going to use differential equations to describe the behavior of these neurons. Yeah? Okay. So let's see how this actually works. In the red box here, we're going to just start this today and we'll finish it next time. You'll see a whole bunch of white space on the right-hand side here. That's intentional. We're going to start adding terms as we go. So if you're annotating this, make sure to leave the same amount of space as you see on the slide. We're going to introduce a variable here, y sub i, which is going to represent the value of neuron I. So we have a neural network. We have a CTRNN. That CTRNN has multiple neurons inside of it. And we're going to track continuously changing values in each neuron. So each neuron is going to be assigned its own differential equation. But instead of writing all of them, we're going to write just one, which represents the same equation, which lives at every neuron. Yeah? So we're going to describe the rate of change of the ith neuron, and we're going to build up a description of how it changes over time. And we're going to start by adding this first term, which is minus y sub I. Seems like kind of an odd thing to do. For those of you that are more comfortable with differential equations, what does this mean about the behavior of the ith neuron? Let's describe the value of y as the value of y sub I. We want to look at how this value changes as a function of time. For our purposes, let's assume that the value of the neuron can range between -1 and +1. What does this differential equation tell you at the moment about the behavior of this neuron? No intuitions yet? Remember that usually when we're describing something that's changing over time, if you want to build up an intuition, it usually helps by starting by setting some initial value. So let's say at some particular point in time, the ith neuron in the neural network has a value of +1. As we start to move forward in time continuously, because we're dealing with differential equations, how does this value change over time? It goes to 0. Okay, so we have the current value of y sub I, and we're subtracting some amount of it from the rate of change, right? So the rate of change of y sub I equals -1. So the rate of change is going down, which means it's going to decrease. This is not a difference equation, so it doesn't mean subtract -1. It just means that the rate decreases by some amount. So at the next time step, let's say the value of the neuron, it's changing continuously, but because we're going to be working with computers, we're going to read out these values at discrete times, is now 0.9. What happens at the next time interval? It continues to drop continuously, but when we read out at the next time interval, what do we see? 0.8, 0, 0.81 seems like a good guess, right? You'll notice that the decrease is less than the decrease in the previous time interval, because now the rate of change of y sub I is proportional to not -1, but to -0.9. So the rate of decrease is decreasing. If we integrate this over time and we run this out to infinity, at infinity it gets to 0, but what is the shape of the curve? It's exponentially decaying, right? It is decreasing down towards 0. The neurons in your head, when they fire, when they do their work, after a while, if they're influenced too much, they need some time to rest. They will, without any other incoming signals, a neuron will decrease back to its default behavior, which is complicated, but for our purposes, let's assume it's 0. So a neuron does some work. It's stimulated by something, and then it's no longer stimulated. It exponentially decays back towards its default state. So as you'll see next time, we're going to add additional math, which introduces a better model of what real neurons do than the neurons you've seen so far. I think we'll stop there. You have a quiz due tonight. Undergrads, you're working on assignment 4. Grads, you're working on 7 and 8. I'll see you on Thursday.